Well, hello, my dear friends from the Theosophical Lodge. I'm glad to be here with you tonight. This is going to be one more in my kind of informal and a little bit mathematical, but also mostly talking discussions about what we know and also what we're learning about the nature of space and time. I jokingly gave a title for this that said Space and Time, a Wrap. And it's not going to be that. This is a continuation. I'll get a little further in developing some of the ideas of relativity. And these will be shifting tonight from the ideas of special relativity to general relativity. And then towards the end, I'm going to talk also and bring in some of the philosophical concepts and then more recent and important and deep questions about the nature of space and time. So what I'll be discussing here tonight really is going to be stuff that took place with Isaac Newton and Albert Einstein running from about the late 1600s up into the early 1900s. But that's not all I'll be talking about. I'll bring us into the 20th and 21st centuries as well as we go on this evening and then in talks to come. First, just a little bit of a review, if I might. One of the times I talked about all this space-time stuff and relativity, the last couple of lectures, we went through an actual mathematical derivation that involved some kind of actual algebra and stuff. You might remember this particular drawing, which I burdened you with a couple times ago. This was talking about a space-time diagram. There along that vertical axis, we see time multiplied by the speed of light. That's called the time axis. Along x, the horizontal, we have distance. And we went through a derivation of something called the twin paradox, or the notion that if you're sitting still in space for a certain period of time, but a twin, let's say, zooms away at some significant fraction of the speed of light for a while, turns around, and comes back, what we discovered because of a mathematical structure that Albert Einstein gave us was that using a device called the space-time interval. Space-time interval was a special way of accounting for space and time. And it says delta s squared there is equal to c times delta t minus delta x squared minus delta y squared minus delta z squared. That was a device that he came up with by applying the two fundamental postulates of special relativity. Those were that the speed of light is the same in all reference frames, and the laws of physics are the same in all reference frames. He was a smart enough guy to sit around and think about what that meant, and he intuited, leapt to, came up with the idea that space and time are not distinct. They're somehow tied up with each other. And he invented this accounting tool, essentially, a space-time interval. And what you can prove is that sitting at rest, your space-time interval will be maximal. If you change some of your motion through time into motion through space, as in the twin that goes away and comes back, the total space-time interval for the traveling person will be shorter than the space-time interval traversed by the stationary person. How can that be? Well, what we reasoned through was that this absolutely demanded that from our perspective in our reference frame, sitting still on the surface of Earth, well, not still on the surface of Earth, but apparently still, from our perspective, the traveling twin's clock had to slow down so that that twin in the traveling spaceship would experience the same laws of physics as us, meaning that as far as he was concerned, his clock was running at a normal rate. Laws of physics were the same because clock rate depends on the laws of physics. And yet it's proven, it's known now by experiments using radioactive decaying particles actually, that in fact traveling clocks do slow time down, and a twin who makes an excursion and comes back will have aged less. According to us, our eyes, the way they look when they show up. But to them, their clock was running at a normal rate. I went through it in more detail in the initial presentation. Hopefully what I've just said there is enough to jog it in your memory. And it's such a profound thing. It's really worth admiring the fact that Albert Einstein was able to use his intuition and then create the mathematical structure from that, which was this space-time interval idea, and allow us to explain reality at a level and in a way that had not been possible before. Some of the things that came from special relativity was the idea of relativity of simultaneity. We think we know what the word simultaneous means, but the word simultaneous falls apart when you allow reference frames to move relative to each other and the velocities become any significant fraction of the speed of light. So that's a crack in the head and a very interesting application of the first set of ideas that Einstein came upon. Those were published in 1905. So what we're going to do now is move away from the constraint of special relativity, which was inertial reference frames, meaning frames of reference, whether moving or not, that are not experiencing acceleration. So their rate of motion is constant. Everything gets different and much more complicated if you go to accelerating reference frames. So in our last meeting together, I spent a while talking about acceleration and what that was, and I mentioned that acceleration is the time rate of change of velocity, velocity being the time rate of change of position. Once we're in an accelerating frame, it's called a non-inertial frame. It means that velocity is inconstant. And this word acceleration, I'm going to drop back and review another little bit of history here because it's important and it's going to help me to illuminate the full depths of these concepts. It was in 1687 that Isaac Newton published this big giant tome of a book which he'd been working on for many years. But back then, academicians didn't have to publish every 2 months in order to get grants. He could work on a book called the Principia for years and then lay it on the world and let them spend the next 50 catching up with him, which is sort of what happened. So in the Principia, Isaac Newton develops 3 laws of motion. And if you had a high school physics class, you would have heard what some of these are, or you may have absorbed by osmosis. And the first one, Newton's first law, is really just the law of inertia. It's the one that says a body at rest tends to remain at rest. A body in motion tends to remain in motion unless acted upon by some outside force. Okay. Now, to what extent does it want to stay at rest or stay in motion? Well, that turns out to depend on its mass. And it was consideration of that idea that led to then Newton's second law. And I've shown you this before, so it should look sort of familiar. First, let's just look at the basic statement of it. So this would be Newton's second law. It says force is equal to mass times acceleration. force is measured in a unit called the Newton at this point in time. That breaks down into units of meters times kilograms per second squared. If you look at that and then reach for a little algebra, you can see how in the second box down I've rearranged that a little bit. I said, well, we could say that acceleration is equal to force divided by mass. So think about that. That's a mathematical statement of something we call direct proportionality. So if we consider holding some things constant and changing other things, from this middle box, acceleration equals force divided by mass, that means if we kept the mass constant but double the force on some object, the acceleration would double. If we kept the force constant and doubled the mass, because that's in the denominator, it means that the observed acceleration would drop in half, right? Hopefully that's a pretty easy leap to make. That's direct proportionality. Now, let's look at the bottom box. It's the one I wanted to get to and kind of focus on. I've rearranged it by algebra. It just says mass is now equal to force divided by acceleration. What that says, if you stop to think about it, we can measure mass. As long as we can control quantitatively forces and control or measure their accelerations, the resulting accelerations. We use a known force on some body and measure its acceleration. We got two numbers. We divide the force that we applied by the acceleration that we observed, and we can calculate the mass. So think about that. And where's it coming from? Now, let me mention that this force can be derived in a general way. It can be due to holding up a magnet on a piece of metal. It can be force exerted by an electric field, say between two plates, on a charged particle, like an electron or a proton, let's say. I could keep going. There's multiple ways to apply forces and then observe the acceleration that results. And from that we can compute a mass. That mass is what we would call an inertial mass. Excuse me. It would be the mass that we measure by virtue of this object's tendency to resist acceleration. To get a larger acceleration, you have to apply a larger force. Pretty simple concept. But note, I'm saying it's an inertial mass. That's kind of a crucial point, and I'll be making that obvious as I go along here. I hope obvious. Now, later in the big book of All Physical Facts That Matter, per Isaac Newton in the mid-1600s, he laid on the world, was really one of the greatest leaps and achievements in the book, the Principia. And that was, it's called Newton's Universal Law of Gravitation. And it's quite a different beast. And involved, this is the one that supposedly came to him in an idea as he watched an apple fall out of a tree in his garden one day, and he had a flash of insight, and he thought, apples falling towards the earth, why does the moon hang in the sky? And he knew enough about his previous work and laws of centripetal acceleration, centripetal motion, circular motion, and he had a flash, and he thought, there seems to be a force that matter exerts on each other, attracts each other, and he came up with the universal law of gravitation. Now, it's a little bit more complicated algebraically. Newton's force of gravity would be equal to this big letter G, which is called the universal gravitational constant, and I listed what it is numerically, times the mass of body 1 times the mass of body 2, divided by the distance between their centers, as listed in the denominator as R12, and that is squared, meaning that the force of two massive bodies exerted on each other is proportional to 1 over the distance squared. That's an example of something we call an inverse square law. And those happen all over the place in nature. It's very commonly encountered. But this was one of the first ones quantified and actually understood. And it was an incredible leap by Newton. So one of the things that comes from this, for example, if you apply Newton's law and do some more work and fool around with it and think about, well, suppose, an object on the surface of the Earth, its radius is trivial compared to the Earth. Let's plug in the mass of the Earth, the radius of the Earth, and then the big constant g, and just ask a question of what's the force due to gravity on anything sitting on the surface of the Earth. And that is how one can quickly derive what is known, and you might know this number even, the acceleration due to gravity on the surface of the Earth. Turns out that if you just drop anything on the surface of the Earth, it will accelerate downward at a rate of 9.8 meters per second, meaning that it compounds and it goes faster and faster. That's the acceleration due to gravity. And it doesn't depend on the size of the mass you're using, because that mass drops out when you do a little bit more complicated algebra. The other way of saying that is 32 feet per second, and you may have heard the acceleration of gravity on the surface of the Earth referred to that way. What I want to get to now, though, is using that law and doing a rearrangement of it as I did before. So, you see bolded word algebra, and I'm applying it to Newton's law of gravitation. What I could say now is that if I knew the force of gravity is another word for weight, and I knew the radius between that object and the center of the Earth, and I knew the mass of the Earth, that's m2 in the denominator. So if I knew all that stuff, I could measure mass 1. And people figured that out, and they immediately started doing those kinds of calculations and measuring masses by weighing them. They had been doing that all along, not really fully realizing the assumptions being made, but now they're doing it knowingly. You could take a mass, 1, that you measured first by inertial methods, applying a known force, observing the acceleration that we talked about a minute ago. Now you take a mass 1 and see how these other numbers all sort themselves out in the expression there on your right. This worked every time. And that's kind of a big deal, because what it illustrated was that inertial mass and gravitational mass are the same. That was now describable and provable, but nobody really knew why. And they didn't immediately have a good way to test Newton's law of gravitation. So I wanted to mention the fact that there was a beautiful experiment that finally got done in about 1889 by a fellow named Henry Cavendish. And I didn't quite get all the way through my exercise of drawing for you the apparatus, but I'm hoping this will be legible enough. What Henry Cavendish did was take a long, slender thread that had a known torsional stiffness, suspend from it a rod that you put a small mass m on either end of that rod, and then you would You would measure its position, you'd see where it was hanging, and various ways to do that. They actually had to build whole buildings to do this, and then look at the stuff through telescopes because they didn't want to be close enough to it to disturb it with wind. Then what you would do would be to move up those masses, M2, on either side. So it's in a balanced arrangement, and it's going to pull the rod towards them in a mutually self-reinforcing fashion. So you've got the little masses hanging by a thread with nothing around it. You measure the position of this rod. Then you bring in up these other two masses on either side. And what would happen is that rod would swing so that the little masses would swing towards the now inserted larger masses, M2. Well, mass of M1, M2 was known, and from all this, they could prove that Newton's law of gravitation worked on everything. It didn't have to be the Earth. That was a handy object, and early experiments used it. But in fact, you could validate everything about that big funny-looking law using this thing called a Cavendish balance. That was done in the late 1800s. You might imagine that the technology has come a little ways since then, and we've found other ways to validate universal law of gravitation, and it holds up. It works every time. Amazing achievement, and kind of an experimental tour de force. That's why I wanted to bother you with that. I've looked at actual pictures of what this apparatus looked like, and it was, it was a mess. It took a whole small building to do it, observing through microscopes. Couldn't be any wind currents, very fine measurements. This thing doesn't move a lot, but they were able to nail down the value of large G, the gravitational constant. So kudos to the old scientist. I'm impressed anyway. So with all that, I'm focusing back onto this sort of fundamental idea and the fun idea of inertial mass being the same as gravitational mass. This still doesn't say where inertia comes from. That was up for grabs. At about the same time, in the late 1800s, people were puzzling over inertia. Okay, it's the same as gravitational mass. Where does it come from? There was a scientist named Ernst Mach who did a lot of thinking about this. And one of his main devices is one with the spinning bucket. You put a bucket on a string and you wind it up, put some water in the bucket, it spins, and the water kind of moves out and makes a parabola and then stays that way for a while as the bucket spins down and it stops spinning. And Mach was thinking about, well, okay, that's inertia. You've also seen me illustrate the idea, if I talk about you throw a pencil through the air, it keeps going through the air. How does it know where to go? What causes it to keep its orientation? Mach ended up deciding that the only way this could be explainable would be if there was some kind of a connection between the mass and the rest of the universe and the local frame where people are doing these observations and making these measurements. Somehow, the matter distribution all the way out to the infinitely distant stars was feeding information into the local situation as far as establishing inertia. That, he didn't know the mechanism. All he could do was conclude that there must be something doing that. We still don't know what's doing that. People still respect and use and accept Mach's principle. We're working on it. But that was the state of the thinking on this as Einstein came along in the late 1800s and started then working on relativity leading up to his paper in 1905. what it allowed him to do was think about reference frames. It got him thinking about all that, and allowed then for the invention of special relativity. Um, as I said, that was all worked out, and what we're going to now do is go over into and discuss what happens when you lift the constraints and you start thinking about accelerating frames. Well, one of the key steps along the way, in fact, the key thing for Einstein to move from special relativity of inertial frames to the much more complicated situation of accelerating frames was he came up with a crucial insight which we call the equivalence principle. The equivalence principle of general relativity is one of three principles that underlie it. It's the only one I'm going to mention here tonight. And Einstein referred to this as the happiest moment in his life when he hit upon the equivalence principle. And the apocryphal story has it that it came to him sort of in a flash when he was looking at a workman on a ladder or painting a building or something, and he thought about what would happen if that workman fell off that ladder. Well, he'd be in free fall, accelerating towards the earth. But, that, as far as he could tell, the way that would feel until he hit wouldn't be any different than the same guy floating in a spaceship out in interstellar space, where there are no forces doing anything to. What he realized was that there was an equivalence such that the following would always be true: that the physical behavior of objects in a gravitational field cannot be distinguished from behavior in an accelerating reference frame. So this is kind of turning it on its head. And I can help you to understand this a little bit with a drawing, all right? So this is one of the drawings. Well, what I've done here is I've abstracted a sort of a crude version of an idea. So what we have here is a rocket ship accelerating upward. You can see the flames coming out the bottom there, okay? So this thing is accelerating upward at some rate of meters per second. Now, let's imagine the following. Somebody shines a light ray in from the side, and there's a hole in the side, maybe a window. So the light goes through. And let's further assume that someone inside this spaceship is standing there and they can see this light ray go through, and they notice that when the ship is accelerating, the light ray is deflected downwards a little bit. The ship is accelerating, they feel weight. And, the light ray dips a little bit. Turn off the motor. Now the light ray just goes straight level across the ship. Motor on. Oh, I feel weight. The light ray bends. Motor off, vice versa. And it was playing with that idea that allowed Einstein to unlock everything that came next, which was the notion of curved spacetime and the idea that something about mass provides something that's the same as acceleration, and either way you do it, you can deflect a light beam. Let me try to explain that just a little bit more. Why would that light beam deflect downward when the engine is on? Well, there's a time lag. When the light comes in from one side and traverses across the spaceship, because the ship is accelerating, during that period of time, its upward velocity is increasing, therefore the ship moves. And that causes it to look like the light was deflected downwards. Einstein, being brilliant enough, was able to derive from that the notion that what we feel as gravity has to do with what mass does to the fabric of space and time. And that was at least stepping towards an explanation of what Newton had simply described. Newton's laws are descriptive, they're not explanatory. He didn't have the equipment to do the explaining. But that's the difference. That's what Einstein was bringing into this. And it's always a big step in science. Science usually starts off as something descriptive. Eventually, hopefully, it becomes explanatory of what we see. Well, this idea that a gravitational field then, by virtue of curving space and time, would deflect a light beam was hard to test. It was an idea in Einstein's head, and it kind of stayed in his head from when he published it in 1915 all the way until 1919, when a famous British astronomer, a guy named Sir Arthur Eddington, did the famous experiment. Now, this is a very crude drawing, but here's the situation. I've got the Earth on one side, the moon creating an eclipse of the sun. Eddington had to go off into some tropical island someplace and set up telescopes. I think it was in the Caribbean. Wait for an eclipse of the sun by the moon so that he could see the stars on either side of the eclipsed sun. And what he was looking for was a deflection. So if star maps were very well developed back then, people really knew how they worked, what they were, and the positions of stars were mapped out to high precision. So he knew exactly which stars would be close to the eclipsed sun in the sky when this eclipse happened. And he set up telescopes with very high precision measuring capacity. What he was looking for is the other thing I'm trying to depict in this picture here. Suppose there's a star shining its light from the lower position there, so that the light would graze the sun and head off into space. But because of the gravitational pull of the sun, or rather the warping of space and time by the sun, that light got bent a little bit. It would be swung around and then graze by the moon and then come into your eye or your telescope as where you were sitting on Earth. But it would look a little bit shifted out from its actual position. So it would appear to be shifted against the even farther away stars. And that was the prediction. Einstein qualitatively predicted the idea in about 1915 and subsequently came up with a precise calculation as to how much the deflection of light should be due to gravity. And that was what Eddington validated in 1919. And that was when it all broke loose. Einstein was already pretty famous and influential, but when this experiment validated and quantitatively proved the tenets of general relativity, that there's something going on between gravity and light. That was such an outlandish, ridiculous sounding proposition to most physicists of the time. And when he got proved right about that, suddenly he was the man. He was the rock star of physics at that point, because he had fundamentally changed our concept of space and time. And the interplay between matter and this space-time continuum that he had proven to be a thing back in the early 1900s, in 1905, with his big paper on special relativity. Now, before I go on with that, I want to drop back and get a little bit historical about something else, because things have come a long way since then. And I think what I'm going to do now is give you a sort of a preview of what I'll pick up with next time. I don't know if it'll be the very next talk, but it'll be a talk to come in sometime in the next year. Newton had a colleague, not really a colleague, more of a competitor, Newton and this guy didn't really like each other. This guy's name was Gottfried Leibniz. He was a little older than Newton. He was the reigning physicist, or doctor of philosophy, as they called him back then, natural philosopher in Germany, about the same time as Newton was the reigning physicist in England. He was a little older, a little bit more established. Now, let's talk about space-time and concepts of space-time. Newton pictured space-time in a way that we now refer to as classically. He thought of this space and time thing essentially as a big empty box. It was space. Big, flat, empty box, no curvature, nothing weird. Time is just a thing that keeps happening, tick, 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 simultaneously everywhere, all over the whole universe. And space doesn't care if there's anything in it or not. It's the same, whether it's empty or whether it has really massive objects in it. Objects behaved relationally in the sense that when they hit, or if their magnetic fields interacted or what have you, then they would have influences on each other, but they weren't really influencing the space they were in. That was a neutral interaction. Leibniz, on the other hand, had a very different way of looking at this. He eventually lost the argument. They had a big argument because in his Principia book, Newton essentially presented calculus as a now worked out field of mathematics and claimed it for his own. Leibniz had also invented calculus, the field of mathematics, a little bit before Newton. So they were just not on great terms. Well, Leibniz also had a concept of space and time and objects that was very substantially and interestingly different. Leibniz thought of objects as existing on their own somehow and having space somehow encoded in them. I don't know what he said about time, but when it comes to the notion of space, Leibniz contemplated space as something that arose, emerged, due to fundamental interactions between objects. And in that sense, it was a radical difference from Newton's idea of a big box-like container, no particular concern about what was in it. Leibniz even went on to suggest in a slightly different context that space might really just be in the mind. Somehow there was something going on between objects. He didn't call them quantum objects. They didn't know about that then. Just masses that encoded, unfolded, emerged as what seemed like space to us. He couldn't really wrap that in mathematical language. It was his intuition. And what's so remarkable about that, and where I will go next time I pick up on topics in space and time, is the fact that now, in the 20th and 21st centuries, that's starting to look to be right. Leibniz somehow mentally time traveled into the future and picked up one of the key fundamental insights of modern research on quantum mechanics and space and time. It's now looking very much plausible. It's not proven, let's just say plausible to the deepest thinkers of our time now that space is an emergent property. It's actually not as fundamental as even Einstein thought it was. As much as Einstein moved us along, helped us to understand the way in which space and time are jumbled up with each other, and the way in which matter and the mass associated with matter can bend space and time and slow the flow of time down. it's even more radical than that. It's now looking very plausible that what we think of as a short distance has to do with the degree of quantum entanglement and quantum correlations taking place between some kind of objects. We don't even quite know how to completely explain them. One of the physicists uses the word amplitude-hedron. But there's quantum correlations between parts of space-time, and they seem close to each other. Less correlations at a quantum level that is happening in however many dimensions we don't know. 11 dimensions, that's up for grabs. But fewer correlations, less quantum entanglement, things will seem farther apart. That is now a hotly debated and big idea in physics, and that's what I'll be trying to take us to next time we work on these topics together. And it's certainly a mind blower. So just kind of chew on that. And it's beautiful to see how the flow of ideas and brilliant individuals intuiting and grabbing things out of nowhere in some cases, like Leibniz. Falls to disfavor, probably got ridiculed, then rises again later, 3 centuries, 4 centuries later. That's quite a biggie. So anyway, I hope you guys are doing well, and wish you all well. And we will convene again next quarter and have another science night together. Thank you, and goodbye.